We may have a problem that a given matrix has no real eigenvalues, only imaginary eigenvalues. Let me illustrate this case by the following example. X derivative is x plus 3y, and y derivative is minus 6x minus 5y. So we write the matrix A, which is in this case 1, 3, minus 6, minus 5. We compute the trace of this matrix. 1 minus 5 is minus 4. And we compute the determinant of this matrix, which is minus 5 plus 18, which is 13. Then the characteristic equation is lambda square plus 4 lambda plus 13 is 0. Then the solution, lambda 1, 2, can be written as minus b half plus or minus square root b half square minus ac. But now 4 minus 13 is minus 9. And square root of minus 9 is not a real number, but we can use I, the imaginary unit, and then we can write it as minus 2 plus or minus 3I. Square root of 9 is 3, and square root of minus 1 can be written as I. Well, and now we can proceed in a similar way as before. Just if we consider lambda 1 or lambda 2, then everything will be the same up to the sign in front of each I. So we don't have to repeat the computation twice. We can solve only using lambda 1. So for lambda 1, let's choose the sign plus. This is not important. You can choose any sign you wish. Minus 2 plus 3i. Now we want to find the corresponding eigenvector. So we build the matrix A minus lambda 1e. That means we subtract this number from each entry on the main diagonal. 1 minus 2 plus 3, 3 minus 6, and minus 5 minus bracket minus 2 plus 3i. So we have minus times minus is plus, 1 plus 2 is 3, minus 3i, 3 minus 6, and here we have minus 5 plus 2 minus 3i, which is minus 3 minus 3i. And then, similarly as before, we want to find the eigenvector b, which is in the null space of this matrix. That means if you multiply this matrix by the eigenvector from the right, you get 0. That means the scalar product of this line with the vector should be 0. And this is easily obtained when we swap these two numbers and we multiply one of them with minus 1, which would give 3. And if we multiply this minus 1, we have 3i minus 3. But we can divide by 3. And we have 1 minus I. Because if we have some eigenvector, then any non-zero multiple is again a perfect eigenvector. So we can multiply by 1/3. Well, and And now we have the solution v1 e2 lambda 1t. But this is a complex solution, and if we have a real linear homogeneous equation having complex solution, then the real part of the solution is again a solution of the system, and the imaginary part alone is again a solution of the system. So we want to find the real part and then the imaginary part of this complex solution. So for this purpose, we use the values that we have found. V1 is 1 minus I, and here we have E2, and lambda 1 was minus 2 plus 3I times t. If we expand this multiplication, and if we use the property that E2a plus b is E2a times E2b, that means the addition index exponent corresponds to multiplication on the line. And if we use further that E2 I phi is cosine of phi plus I sine of phi, then we can write this as 1 minus I E2 minus 2t. This will be a real multiplicative factor that will appear in each term, and E2 3it can be written using this formula as cosine of 3t plus I sine of 3t. Well, and then the real part is, so E2 minus 2t is everywhere. The first component is 1 times this bracket, and the real part is cosine of 3t. And the real part of the second component is, if we expand this multiplication with this bracket, then we have 1 times cosine, which is cosine of 3t. Then 1 times I sine will be imaginary, minus I times cosine will be imaginary. We will write imaginary terms in a second. Now we want to collect the real part. And I times I is minus 1, times minus is plus 1, sine of 3t. So this is the real part of this solution. Now let's consider the imaginary part. E2 minus 2t will be everywhere. And the imaginary part in the first component. 1 times cosine is real, that's already here, and 1 times I sine gives the imaginary part, namely sine 3t. And in the second component, when we multiply 1 minus I with this bracket, then 1 times cosine is real, that's already here. 1 times I sine gives the imaginary part, which is sine 3t, minus I times cosine gives the imaginary part, and that will be minus cosine of 3t, and this will give the real part, which is already here. So this is the real part, this is the imaginary part. Each one solved the system, and they are already real expressions. We can multiply with any constant, and we can add, and this is the real general solution of the system, let's call it Z. So to sum up, once again, if we have a system like that, we write the matrix, we write the trace determinant, we build the characteristic equation, and if it turns out that the characteristic equation has imaginary roots, then we consider just one of them. We build the matrix A minus lambda 1e, and we find the corresponding imaginary eigenvector. And then having the eigenvector and eigenvalue, this is the solution. Using the numerical values, we can write the expression. And then we build the real part of this complex solution. We build the imaginary part, and the general linear combination of them is the general solution, which is real to the original system. And having the initial condition, we can find the values for the integration constants C1 and C2.